Okay, in this video we'll be going through the basics of simple harmonic motion. Simple harmonic motion is a completely different type of motion that we have previously seen in NCEA physics. We can describe simple harmonic motion as a oscillatory motion, right? And this just means that the object is oscillating, right? And the reason why this motion is unique and we haven't seen it before in NCEA is because this motion has a varying displacement. It also has a varying velocity and also a varying acceleration. Okay, and it's really these two factors, the varying displacement and the varying acceleration, that makes simple harmonic motion different. We've encountered varying velocity before, that's our kinematics, but usually when we talk about kinematics, we're under constant acceleration. This is, I think, the first time where we're encountering changes in acceleration in NCEA. The nice thing is that these things vary in a sinusoidal pattern, so they're very easy to model. And so what that means is we can just graph it with a sine or cosine curve, right? So I'm going to use a very, very simple example to show the relationship between the motion and the sine curve. So for this example, we're going to put a mass on a spring, right? So like this, okay? So this is a spring and this is a mass, okay? And I'm going to show this spring in a range of different positions and time intervals, okay? And so it's going to be like that, okay? So spring and spring, spring, spring. Now, just to be clear, these aren't different springs and masses. These are the same exact spring and mass, just at different time intervals. So as we go across here, we are changing in time, okay? So we can label this position 1, position 2, position 3, position 4, and position 5 just goes back to position 1, so we can just call that position 1, okay? Now, I'm sure you can imagine if we have a mass hanging from the ceiling and we pull it down slightly, it's going to bounce up and down like this. So that's kind of what I tried to show in this depiction. And so this line right here is the mean position, right? So we can call that the mean right there, okay? And so what I'm going to do is I'm going to write some different values for these varying quantities, okay? So let's start off with displacement. So as you can see here at point number 1, we are starting at the mean position. And so therefore our displacement is going to be 0, right? And then as this mass moves upwards, right, to point number 2, the displacement is positive A. Okay, and what I mean by A is the amplitude. And amplitude is another word for max displacement. Okay, and the reason why I called it positive A is because we are going to define upwards as the positive direction. Okay, and then as you can see here, at point number 3, the mass has moved downwards again. And we are back at the mean position, so our displacement is now equal to 0 once more. And our mass continues to move down to point number 4. And as you can see here, we are at max displacement again. However, we are in the opposite direction, right? We considered up to be positive, and now we are moving downwards. And so this is negative A, right? And then we move up once more to the mean, and so our displacement is 0 once again, because we're at the mean. So now, when we talk about the velocity, let's start off with the max displacement region. So that's point number 4 and point number 2, because I feel like that's going to be easier to explain. If we imagine the spring mass system and we pull it down, okay, and it's oscillating, when it goes to the bottom, we can imagine that it's going to pause there for a fraction of a second, right, at the bottom. And so if the mass pauses at the bottom momentarily before going up, we can say that the velocity at the bottom is going to be 0. And very similar situation at the top, so at point number 2, when it's at the top, it's going to pause momentarily before coming back down. And so at the top, the velocity is also 0. The velocity at the mean position is a different story, so this might be easier if I extend this outwards again. So like so. Okay, and this is point number 2 once more. You can see it's the exact same situation. Okay, we have the velocity is 0 momentarily at point number 4, and then it accelerates upwards to the mean position, and then once it's at the mean position at point number 1, it's going to slow down again to velocity is equal to 0, right? Because we established that the velocity is 0 at point number 2, and so this is point number 2 once more. So the velocity is 0. So it goes from 0 velocity, accelerates upwards, and then slows back down. And so we can imagine that the velocity at the mean position is going to be v max, right? So max velocity. And because in this scenario the mass is moving upwards, we can define that as positive v max because we took upwards as positive as defined here. And so because this is positive v max, this also must be positive v max here. However, for point number 3, this is going to be negative v max. The reason for that is because we are at the opposite scenario as to what we have over here. Over here, the mass moved upwards, came to a rest momentarily before coming back down. And so now the mass is moving downwards, and so the velocity is in the negative direction. Again, because we defined upwards as positive. And so now moving on to acceleration, I believe the best way to explain this is by looking at mass number 3. So if we look at the acceleration of mass number 3, we can see that before it gets to point number 3, it's accelerating downwards, right? So from point 2 to point 3, it's accelerating downwards, okay? However, from point 3 to point 4, we can imagine it's slowing down, and therefore it's accelerating upwards, right? If we have a mass moving downwards and we want to slow it down, we need to accelerate it upwards, okay? And so over here, we have, like I said, speeding up. But over here, right, we are slowing down. Okay, like I said before, if acceleration is downwards as we go from point 2 to point 3, but then from point 3 to point 4, the acceleration is upwards, that means at some point the acceleration had to switch from moving downwards to moving upwards, okay? And we can imagine at that point that the acceleration switches direction, the acceleration is 0. And this point that the acceleration switches direction is point number 3, and so point number 3, the acceleration is 0, right? So that means that the acceleration at the mean positions is 0. Now, as I stated before, let's go to point number 2. At point number 2, I said that the acceleration is downwards, and this is when the acceleration is the highest, right? We can imagine that if we have a spring, and the spring is super compressed, right? If we compress a spring a lot, we can imagine that there's going to be a large force that wants to push the spring outwards. And so that's a very similar situation that we have here, right? The spring wants to push down on the mass. And so this is where we're going to experience the most acceleration. And in this case, this is negative a max, right? We have negative again because we took up as positive. And in this scenario, like I said over here, the acceleration is downwards. And so it's the opposite situation over here. At point number 4, our acceleration is again max because we're at max displacement, but this is positive a max because, like I said over here, our acceleration is in the upwards direction. And so we can model these varying quantities as trig functions. And so you may be able to see already that the displacement of the spring mass system already follows a sine function, right? And indeed it does. So we can draw that out. We can have our theta here, okay? And we can have our positive amplitude and our negative amplitude over here. If you want to know why this value is theta, I go through that in my reference circle video. But if we were to model our displacement, we can see that when t is equal to 1, our displacement is 0. And so we can start over here. And then we go all the way to positive max displacement, and so that's going to be at this point right here. Then we go back to d is equal to 0, and so that's over here. And then we get to negative max amplitude, and so that's over here. And then we get back to the mean position, so that's over there. And as you can see, we follow the sine curve. Same thing if we were to model our velocity, right? We get positive Vmax, and then we get negative Vmax. Okay, let's just go from over here. We start at positive Vmax, and so we can go right over here. Then we get to V is equal to 0, and so V is equal to 0 right there. And then V is equal to negative Amax, and so that's right over here. And then V is equal to 0 once more, and then V is equal to positive Amax once again. And as you can see, we follow a cos graph, okay? And then finally, we can map our acceleration. So this is positive Amax. This is negative Amax. And as you can see, when we start at the mean, we start at a is equal to 0, so we start right here. And then at point number 2, we get to a is equal to negative a max, and so we go down like this. And then we get to a is equal to 0 once more, as we're at the mean. And then a is equal to positive a max, so we go to the positive. And then a is equal to 0 once more when we reach the mean. So like this. And as you can see, we follow an inverse sine function this time, okay? So the sine function just flipped. Now from our calculus courses, I believe in level 2 calculus, we learned that if we were to differentiate displacement, we get velocity. And we know if we differentiate a sine curve, we get a cosine graph, right? And we also know that if we differentiate velocity, we get acceleration. And we also know if we differentiate a cos graph, we get an inverse sine graph. So mathematically, the relationship between these quantities makes sense. And so from this, we can get our definition of SHM, so the definition of simple harmonic motion. There we go. The first thing is that the object experiences a restoring force. Now, restoring in this case means going back to the mean, so a force that makes the object always come back to the mean, okay? Going back to mean position. Now, this restoring force is proportional to the displacement. Now, what does that mean? That means that the restoring force is going to be larger when the displacement is larger, okay? Now we can see that at point number 4, the displacement is max or negative max because we defined up as positive, but max nonetheless. And we can imagine, in this case, the spring is as stretched as it's going to be. And we can also imagine that as we stretch out a spring, the force that's going to pull it back in is going to be larger, right? As we pull out that spring, it gets harder and harder to pull out. And then same thing over here. This is positive max displacement, and when the spring is compressed, the force that's trying to push it back down is also max. And so that's what it means by proportional to displacement. As the displacement increases, the restoring force also increases. And B, it also has to be in opposite direction to the displacement. Okay? Now, we can simply see that through our acceleration, right? Because as we know, F is equal to ma, and therefore our F is directly proportional to our acceleration. So our acceleration and our velocity vectors are going to be in the same direction. So we can see here, when we are positive max displacement, our acceleration is a negative max. And so you can see, just by simply looking at this, that our displacement and our acceleration are in the opposite directions. Okay, so that's our definition of simple harmonic motion. And just to finish off, I'm going to give you some examples of objects in simple harmonic motion that you can see in NCEA. The first one being a spring hanging from the ceiling, right? That's the exact same scenario that we have up here. We can also have a spring on its side, right? A spring mass system on its side. And this is going to be oscillating left to right. Another example is a pendulum, right? So we have a pendulum, and this ball, or the mass on the pendulum, is going to be swinging from left to right, right? So it's going to be going in this sort of a motion, like this, okay? And occasionally we see a pipe of water, so a U-shaped pipe, and we have water at different levels, right? Different water levels moving up and down, okay? So if you can imagine, these water levels change in simple harmonic motion, like this. And finally, the last example is an LC circuit. Okay, I go into this more in my electricity videos, which if you're watching this as this video is released, I haven't made yet, but I'm assuming you're watching this in a few months' time, so, or maybe a few years' time. So at that point, those videos will be out. But if you're watching this like 5 days after this is released, it hasn't been out yet, okay? LC circuit is when we have a capacitor and an inductor, right? And the charge on the inductor oscillate in simple harmonic motion. And that's it for this first video.